Alright, in this video we're going to discuss the derivative, and we've actually seen this back in Module 2, right when we were discussing local linearity and rates of change, but now we want to take a little bit more of a algebraic approach and formalize the mathematics that go along with the derivative. Okay, so we have a few different objectives here that we hope to complete by the end of the module, and I'll let you read those in your own time. Okay, so just reminding us what we did in Module 2b, we said that the limit of the average rate of change, again, as we decreased the delta x, the step size, to 0. That was actually equal to the instantaneous rate of change of the function at the point A. Okay, so, but in just quickly, the average rate of change was actually, or the limit of the average rate of change was the instantaneous rate of change. Similarly, now we said that the average rate of change, that was the slope of the secant line. So if we took the limit of the slopes of the secant lines, we actually get the slope of the tangent line. So we also connected the ideas of instantaneous rate of change at a point being the slope of the tangent line at the point. Okay, so just a little quick reminder of the demo that we did. This is again a free program called Algebra. Very nice, very handy. And so what we said is if the black line is our function, okay, so, and P and Q are 2 points on the function. So if I determine the line between P and Q, okay, and that's given in blue, that's my secant line, we should, as we move Q towards P, we should end up with the blue line being almost on top of, or on top of, for all practical purposes, on top of the red line, which is the tangent line. So here's my slider, and right now the step size is at 2, and what I'm going to do is I'm going to decrease that step, moving Q closer to P, and we see that the secant line, as we decrease step size, actually gets on top of the red line, the tangent line. Okay, and so for all intensive purposes, we can say that the secant line at this point is the tangent line. But again, we have to technically say that they are, or that the limit is, or the limit of the secant, the limit of the slopes of the secant lines is the slope of the tangent line. Alright, so switching back here, I'll minimize this. Alright, so then now we're going to go through and develop kind of the theory of the derivative. A lot of it we've already seen, but we have to introduce some notation. So I'm going to fix P at an arbitrary point a comma f of a. So it's just pick some x value, call it a, and then f of a is the associated function value. And now x, remember, I moved q towards p, so I'm going to let q vary, and I'm just going to represent that by q f of x, or x comma f of x. So then, remember I said, okay, the limit of the difference of the average rate of change is equal to the instantaneous rate of change, but now I can actually dissect this a little bit further. So remember, average rate of change was the difference in the y values over the difference in the x values, and when I do this, I actually have to let one value approach the other, and it doesn't matter which one you do here, it'll end up being the same either way. And then when I go a step further, now using q and p, that changes my notation to f of x minus f of a all over x minus a, and I'm letting x now approach a because remember I said I want to take x, I want to take q and move it closer to p, so I'm letting x approach a, and when I do that, I get this result. Okay, and this result is, we call that the derivative of the function at x is equal to a. Okay, and this we've already seen, so this is just saying the limit at, or really the average rate of change, the limit as we let x get close to a, is going to be the derivative at the point. Okay, and so remember we talked about this just moments ago. The instantaneous rate of change, slope of the tangent line are both equivalent, and both can be determined from this expression. Okay. Now there is another way to communicate this idea of a derivative, and that's using Leibniz notation. So remember, way back in Module 1 we introduced prime notation, and so that's what this is in. Now the other type of notation, which will be useful later on in Module 3, is called Leibniz notation. And this is read df over dx evaluated at x is equal to a. And that's the same thing as writing f prime of x is equal to, or f prime of a. Again, this notation will be easier for us to use initially, but when we get into multivariable equations, so equations with more than one independent variable, we will need to use Leibniz notation to distinguish between these concepts. Okay. And now one last view of the derivative, and this gets a little algebraic or algebra intense, so feel free to pause the video when you need to. But if I let delta x equal h, I get this string of equalities. So again, this is the same as what we started with. And now I'm going to represent this delta y. Remember, delta y was just the function value at a point and then some small step. And so before, we remember up here we said it was just y2 minus y1. But if I take the two function values to be really close to each other, that I can represent by just a little change in x, which I can denote symbolically as delta x. Okay, so I have y2 minus y1 over x2 minus x1. Same idea as before. And now what I do is I can do a little bit of algebra. Okay, so down in the denominator, the a and the minus a will cancel, and I'll be left with delta x. But again, I'm letting delta x equal h, and we'll see why in a moment here. And so when I go to this stage over here, I replace all the delta x's by h, and I get limit as h approaches 0 of f of a plus h minus f of a all over h. Now the reason we change it to h really is just so we don't have to write more. Nothing spectacular behind it, but this idea we've seen before, and it is actually the difference quotient from pre-calculus. So the limit, or the difference quotient at a point A. But really, that's the nice thing, and that's really the whole idea why we introduced the idea of a difference quotient in pre-calculus, was to prepare us to do this sort of computation. And so as a result, now we have many different forms of the derivative, all of which you can see here, and they are all equivalent. Okay, so in the next video we will work on using this mathematical language to actually determine the derivative at a point. This video was just mainly to introduce the theory and explain why, where this stuff is coming from, and why we care about the derivative. So stay tuned for the next video on computing a derivative at a point.